Okay, so this will be the prep video for sign charts. So for those of you who are using this to figure out kind of how this partially flipped classroom is going to work for Math 270, the idea is that I will put together a video. I try and keep them to like 5 to 15 minutes. The idea being to introduce the concept, do a couple of simple examples, and then you do a couple of very simple problems, just to kind of get your feet wet with the concept. I find that your brain actually is thinking about things all the time, whether you're sort of consciously doing that or not. And so to have, a little more time with the concept on board before we actually start hitting the harder problems in class, I think tends to lend itself to better and quicker understanding. So that's the game plan. Also know that there are notes on Blackboard so that you can actually see the notes that I'm working from, so if you want to print those out. Although I do recommend that you actually handwrite notes. The research shows that actually writing it out yourself, rather than simply reading it, helps cement the knowledge for you. So, okay, so let's get started. So we're going to start with sign charts. Sign charts, I think, they're actually kind of cool. You're going to hear me say that a lot. Sign charts are essentially a compressed XY axis. So we can graph something like f of x equals x squared minus 4. We know it's a parabola, it's shifted down by 4. We know that its x-intercepts are plus and minus 2. So we can graph that here. So okay, so I know that this thing looks something like this. Okay, so this is a lot of information. We don't know where all the points are, but let's say we didn't actually need the graph. We needed to know less information than that. One thing that we can look at is we could write this as a table and actually just start writing numbers if we wanted to. We could say, well, at 0 it's -4, at x equals 1 it's -3, at x equals -1 also -3, at 2 it's 0, at 3 it'd be 5, so mirror image over here. At 4, 16 minus 4, 12, it would be 12. So pluses here. So we could go along and actually log all the values. Well, obviously that's tedious and cumbersome, but one thing that we notice is that all the values out here are positive, all the values in here are negative, and all the values out here are positive. So if that's all we needed to know, we could simply write that part. So we can come back over here. I'm going to put in where I know it's 0. And then I know everything up here is positive, and I saw everything down here was negative, and everything up here was positive. So we take it one last step, and the actual sign chart that we're going to use we'll put on, like I say, the values where it goes through 0. And I also like to label these. I recommend that you do that. As we get later into the class, we're going to have multiple sign charts for different pieces of a problem, and so I recommend labeling it so you know which one it is, because that's going to determine where you plug in your values. So I usually end up with something that looks like that. So very compact. So instead of taking a whole graph, I have this summary, which tells me where the function is positive, where it's 0, and where it's negative. That's actually a lot of information. So let's just go over here. This is going to be where I sort of keep a list of important information we'll refer to for class. So a sign chart is really a compressed XY axis. The number line is the x-axis, exactly. And the pluses and minuses are the y values. Clearly not the whole y value, just positive and negative. Okay, so we can see that happens when a function goes through 0, but let's look at a different kind of function. What happens if we look at a rational function? Remember, those typically have asymptotes, so let's look at that behavior. So let's look at this function. F of x equals 1 over the quantity x minus 2. We know that this has a vertical asymptote at 2. You ought to kind of know in your head that this is the graph of 1 over x. And so this would be the graph shifted over to an asymptote at 2. Okay, so again, we're trying to compress the x-axis. What do we know over here? Everything on this side is negative. Everything on this side of the asymptote is positive. So, again, the only thing that I'm putting on the number line, the only thing that's really important in the sign chart is the division between the dividing point between where it's negative and where it's positive. So I'm not going to put the origin on there. I'm just going to put here. And I'm going to leave it as a dotted line to remind myself that there's no point there. Unlike with the previous example where we had zeros, those were actual points, not here. So I have plus, minus. So what does that tell us? In the first example, the zeros were dividing points between positive and negative areas of the graph. Vertical asymptotes also can be dividing points. So let's define some vocabulary. We're going to have something called a partition point. To partition is to separate. So our partition points are anywhere that any zero of the function, I don't mean the number zero of the function or vertical asymptote. Another way to think of that, in fact, let's write it that way. We know that this is where the numerator equals 0, and this is where the denominator equals 0. Okay, so we've got the sign chart that's compressed. We know how to divide between positive and negative. The other thing to remember is, because these are all negative values here, I could pick any one of them to know what sign to put there, right? I could pick 0. In fact, I would pick the easiest number I can find. If I want to know for all the values, x less than 2, what the sign is, because it won't change any other time, right? This is the only place that it changes. I'll put in x equals 0, I get negative 2, I write a negative sign. Okay, so now let's look at solving a problem, and we'll kind of write out a process then for how to solve all of these problems. And you can kind of put it together from that. Okay, so here's an example. We want to solve x squared minus 5x plus 6 is greater than or equal to 0. Okay, well, so the first thing is, if I want to know where it's greater than or equal to 0, positive. If I want to know where it's positive, all I really need to do first is to find out where it's 0, and then maybe I could test some points. I think I can do this with a sign test. So the first thing we'll do, and you don't have to write out this as long as you remember that this is what you're doing, we will find out where it's equal to 0. Those are the partition points, okay? And so we'll have x minus 3, x minus 2. So I have a partition point at 3 and a partition point at 2. Those are the only numbers that go on the number line. The sign chart, remember, is about signs, and so I don't want to put any other points except where I know the sign will change or could change. So now I'm going to label it, and now I need to figure out what the sign is. There are two ways to do this. One is to actually go up here and plug in, say, x equals 4, and actually get the whole value and see if it's positive or negative. That actually turns out to be pretty cumbersome. And so what we do instead is we've got these numbers here, right? So if you want to, you can write them off to the side. Numbers, they're terms. I could plug the 4 in here, or I could plug the 4 into the factored form. Either way, I'll get the same number answer. It's just I can get a sign answer much faster this way. So plug in 4. 4 minus 3, positive. 4 minus 2, positive. Positive times positive, positive. This one we're stuck. I think 2.5 is the best we can do. 2.5 would be a mess to put in here, but over here it's pretty easy. 2.5 minus 3, that's negative. 2.5 minus 2, that's positive. Multiply together, negative. Over here, I think the easiest number is 0. 0 minus 3, negative. 0 minus 2, negative. Negative times negative, positive. So this takes some getting used to, but I strongly encourage you to move to this point because this is much faster than actually plugging in values. And we don't really need to know the values. To answer this question, all we need to know is where it's positive or 0. Here's positive, here's 0. Here's 0, here's positive. So your final answer would be, starting at negative infinity, going up to 2 and including it, together with another piece, which starts at 3 and goes up to infinity. And remember, square brackets mean it includes the point, parentheses, it does not. Okay, so let's fill in a little more detail here. Okay, so let's talk about two more pieces. One are called critical points, and they'll come in the next example. A critical point is any partition point that is in the domain. And that's important. So what that tells you is that a vertical asymptote can never be a critical point. So that we'll keep that there. So now let's look at the process that we're going to go through. For the process, we'll always have, we need to have everything on one side and 0 on the other. Okay, so that's the first thing, is to set the equation equal to 0 on one side. And then factor. Find all your partition points. That's where the numerator and the denominator are 0. So find partition points. And we're going to put those on the number line. Not just the critical values, but any partition point. That's any place where it may change sign, the function. Now we'll test one point in each, in between points, partition points. And then we'll have something that looks like this. And then it's important to remember to actually answer the question. So I'm going to actually write that out, answer the question. Okay, so let's do another example. Oh, I should say, before we move on to a whole other example, that if I had started with x squared minus 5x greater than or equal to -6, that's the exact same problem as the previous one, because the first thing I would do is add 6 to both sides. And now I'm ready to go with the sign chart. Okay, so let's look at this one. F of x is equal to x squared minus x over x plus 2, and I want to know where it is less than or equal to 0. Okay, so what do we need to do? We need to get 0 on one side. Done. We need to factor. That's our next step. So x times x minus 1 over x plus 2. That's our factored form. And from that, we're going to get our partition point. So everywhere the numerator is 0 and everywhere the denominator is 0. So the numerator is 0 at x equals 0. We have to include that one. And x equals 1. So we have a point here and a point here. And we know that the denominator is equal to 0 at -2. And again, I like to put in, the book uses an ND for not defined, that's fine also, but just to make the distinction that this is not a point. Okay, so now we need to pick points in between to test. I always pick the smallest thing I can find, or the easiest one I can find. So 0 and 1 are popular choices. We don't have that option here. I draw them in with arrows to distinguish between my test points and my partition points. Okay, and then the last thing I do, particularly when I have a rational expression, you can end up with 4 or 5 factors easily. And so it gets hard to keep track of all the pluses and minuses. If you want to, again, you can write this over here. You notice that I'm writing it in the same sort of visual orientation that they are in the rational expression. So I'm going to write my pluses and minuses in that same order, that same pattern, so that you can write this or you don't have to. So let's plug in 2. 2 is positive, 2 minus 1, positive, 2 plus 2, positive. 3 positives multiplied together, divided together, positive. Let's try a half. A half is positive. A half minus 1, negative. A half plus 2, sorry, down here, positive. So, altogether, 2 positives and a negative would be a negative. Let's try -1. -1 would be negative. -1 minus 1, negative again. -1 plus 2, positive. 2 negatives and a positive. And then finally, -3. -3. -3 minus 1 more, still negative. -3 plus 2, still negative. Odd number of negatives, negative. So if you want to, if this feels a little bit busy, I don't always have this piece, I don't always have this piece. You can also just simply rewrite it, kind of with the information distilled, if that's a little bit easier. So we have minus, plus, minus, plus. You might think, oh, it always alternates. That's not true. So don't get your hopes up about that. Okay, so we have gotten to the point where we have factored, put our partition points on the number line, tested one point, we have our final sign chart, and now we need to go back and answer the question, which was, where is this less than or equal to 0? So we're looking for everywhere it's negative and everywhere it's 0. So negative here, not 0 here. 0, negative, 0. So that means that we'll have for our final answer, negative infinity up to negative 2, together with, do include these endpoints, 0 and 1. And you should always be able to pick any point in there, go back up in here and test. A point in here would be a half. Well, that actually is, we already tested that. So, okay, so that is our third example. And then lastly, I should say I go a little bit faster in these videos because I don't have people to stop and ask me questions, which I enjoy in class. I find that very helpful. So it may be that you need to pause. You may need to pause the videos now and then just to finish taking notes or to think for a moment, and that's okay. And that's a common thing to want to do. Okay, so our last example is the following. Find the domain for the square root of x squared over x squared plus 1. Okay, so this reviews a couple of different concepts. One is domain. Again, I'm a strong proponent of writing the equation for the restriction. What do we know about a square root? The inside has to be non-negative. Write that down. X squared over x squared plus 1 has to be non-negative. Perfect for sign charts. We're ready to go. So what do we know? We know we need to find partition points. We know that x equals 0 is the 0 is the denominator. X squared plus 1? Not a real number. And we know that because this is always, right, when you square something it becomes non-negative. Non-negative plus 1 is, there's no way to get a negative number out of this. That means there's nowhere for it to hit 0. Okay, so that means all we need to put on is this point at 0. So we'll test. I wrote for 1 and negative 1. And actually, if you look at this, you might see that you don't even really need to plug in. That one's always positive, that one's always positive, but that's always positive. This whole thing's always positive, except at 0 where it hits 0. So we could plug in pieces and we would get that. So I bring this up just to point out that there isn't always a vertical asymptote, and there isn't always this alternating sign. Okay, so lastly, let's just talk briefly about, so kind of to sum up what kind of applications we have for sign charts, and we will have many more going through this class. We're going to, by the end of this class, you will be solid on sign charts. You will do them in your sleep. So I encourage you to get comfortable here and just know that we're going to have a lot of practice. So one is to solve polynomial equations, polynomial inequalities. That's one. And that would be something like f of x greater than 0. But we can also solve ones like f of x greater than g of x by just subtracting off g of x, so we get a 0 on one side. Domain, particularly of square roots. What else? And graphing. I mean, if you just wanted some help knowing where the graph, if it's a complicated graph and you're not doing it with your calculator, you could actually use this to get you some information about where the points are without having to do a lot of actual computation. And then we're going to start using this very directly when we get to limits, and we'll use it again when we're graphing functions using derivatives. So this is kind of a beginning start from algebra and pre-calculus, and then we'll add calculus concepts. So that's it, and so I hope that was useful.